next session in this video. This video, we are going to look at approximate method using the kernel. In our previous video, we look at the approximate method using the free term. That is to approximate Fredholm's integral equation. That is y of s equal to f of s plus lambda integral from a to b k of st y of t dt. In that same session, we use a series to approximate this solution. That is y of s equal to phi naught of s plus lambda phi 1 of s plus lambda square phi 2 of s plus dot 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 plus lambda n phi n of s. To approximate this solution, and in that same video too, we saw that phi naught of s was giving us the free term f of s, and also our phi 1 of s was given in our previous video as integral from a to b k of st phi naught of t dt. Now our phi naught of s is equal to f of s. Then let's interchange s to t. Then you could easily see that our phi naught of t becomes f of t. Now wherever you see phi naught of t, we replace it by f of t. Our phi 1 of s becomes integral from a to b k of st f of t dt. Wherever, now let's rewrite this equation in terms of different variable. We can let's first name this equation as our equation 1 and here as our equation 2. Now we can rewrite it in different variables, like let's interchange all the t's to s. Now this equation becomes integral from a to b k of s f of s ds. And let's interchange the s to s. That means in this section too, we can have phi 1 of s to be equal to integral from a to b k of s t f of t dt. And in our previous session too, we saw that this phi 2 of s was giving us integral from a to b k of s t phi 1 of t dt. Now let's interchange these t's to s. Now we're going to have our phi 2 of s to be equal to integral from a to b k of s phi 1 of s ds. Now you can easily see that we have phi 1 of s here and phi 1 of s here, and so we just substitute this equation into this equation. We are going to have phi 2 of s to be equal to integral from a to b k of s into bracket integral from a to b k of s t f of t dt. Then we have my ds here. Then this same phi 2 of s can be rewritten as, we can send this one inside and bring the dt's out. We're going to have integral from a to b f of t into bracket integral from a to b k of this s comma s, then k of s comma t ds. Then my dt comes outside. Now let's name this equation as our new kernel k2 of s t to be equal to integral of a to b, this k of s comma s k of s comma t ds. Now this is our new kernel. Now we have to substitute this into this equation. So we have to substitute this into this equation. Therefore, our phi 2 of s becomes integral from a to b, then k2 of st, then my f of t dt. We move on to the phi 3. In our previous section, we said that phi 3 of s is the same as integral of a to b k of st phi 2 of t dt. So we have to manipulate this one too. So let's interchange all the t's here to s. I'm going to have our phi 3 of s to be equal to integral of a to b k of st, then phi naught of what? K of s of s, then phi 2 to what? S, and ds. That means we are interchanging what? T, the t's to s. I have phi 2 of s, and having phi of s to be equal to this. Now let's say this, we have phi 2 of s to be equal to this. Then you can interchange the s here to this, the x here to what? S. And I'm going to have phi 2 of s to be equal to integral of a to b k2 of st f of t dt. Now you can simply substitute this phi 2 of s into this equation to obtain our phi 3 of s. Now phi 3 of s becomes integral from a to b k of s comma x, then phi 2 of s becomes into bracket integral from a to b k2 of st f of t dt, then ds. Now let's bring the d's outside and send the ds inside the equation. Our phi 3 of s become integral of a to b, then f of t outside, f of t into bracket integral of a to b, then this k of s will come inside the equation, k of s comma s, then times k2 of s comma t f of ds into bracket dt. Now let's name this equation as our new kernel 3. That is k3 of st to be equal to integral of a to b k of s comma s k2 of st ds. Now let's substitute this k3 into this equation. And we are going to obtain our phi 3 of s. Phi 3 of s to be equal to integral from a to b. Then let's get k3. The k3 of st f of t there dt. Now from this we can easily see that when we are having phi naught, having f of s, phi 1 of s, we are having what? K of st. The k of st is the same as k1 of st. So this is the same as k1 here. So phi 1 of s is giving us k1 of what? St. Then we have our phi 2 of st, which is also giving us our new kernel. K2 of phi 2 of s give us what? K2 of st. Then phi 3 of s is also giving us k3 of what? St. Then we can easily say that we can do this till we get to the n term, phi n of s, which will also give us kn of st f of t dt. Now to find for our kn of st, kn of st. We said that when you are having k3 of st, is the original kernel k of s comma s, then k2 of st. And if you are having k2 of st, you are having the original kernel k of what s comma k1 of st. Now this n, the nth kernel will also give us integral of what a to b, the original kernel k of s comma s, then kn minus 1 st ds is our original kernel. Now let's substitute this phi 3 of s, then phi 2 of s, phi 1 of s, and phi naught into our series solution, which is phi s is equal to phi naught of s plus lambda phi 1 of s plus lambda square phi 2 of s plus lambda cube phi 3 of s plus dot 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 plus lambda n phi n of s. We have phi naught of s, phi 1 of s, phi 2 of s, phi 3 of s up to the n 10. And we said that phi of s, y of s is equal to phi naught of s. And we said phi naught of s is the same as the free term, which is the f of s, which is this f of s. And phi 1 of s is the same as integral from what k1 to what b k of st phi naught of dt. And we had what phi naught of phi 1 of s to be integral of k of st f of t as our equation 1. Now let's substitute all this into this series, into this series. And we have our phi naught of s to be equal to our f of s plus lambda f1 to be equal to integral of a to b, then k1 st f of t dt plus my lambda square integral of a to b, then phi 2 of s. I'm going to have the original kernel, the phi 2 of st, then my f of t dt plus lambda cube integral of a to b, then k3 of st f of t dt plus the nth kernel, the nth term, the phi n of s, lambda n integral of a to b, kn of st f of t dt. Now from this side, we are having y of s to be equal to f of s plus lambda integral of a to b k1 of st f of t dt plus integral of a lambda plus lambda square integral of a to b k2 of st f of t dt plus lambda cube integral of a to b k of 3 of st f of t dt plus dot 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 plus lambda n a to b kn of st f of t dt. Now let's rewrite this again by bringing the one lambda out. Then I'm going to have y of s to be equal to f of s. We are pulling lambda outside plus lambda, then our integral sign a to b. Then we could easily see that here is k1 of what? St. So in a break bracket, k1 of st, then plus what mean it made lambda, there will be one lambda here, so lambda k2 of st, lambda k2 of st plus there will be lambda square here, lambda square k3 of st plus dot dot dot, then plus lambda n minus 1, then kn of st, then all into bracket. Then you can pull the f of t out, all here times what? F of t, then minus dt also outside. Now let gamma of st lambda to be equal to k1 of st plus lambda k2 of st plus lambda square k3 of st plus dot 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 to lambda n minus 1 kn of st. And we are going to sum each of the kernels we have, then including the lambdas. Then we are going to see that this should be equal to this is the same as the summation of n is equal to, from n equal to 1 to infinity, lambda n minus 1, then kn of st. And we are going to call this new gamma, this new function, as our resolvent kernel. Resolvent kernel. And so we have to substitute this resolvent kernel into this equation. We're going to have our y of s to be equal to f of s plus lambda integral from a to b, then the resolvent kernel, which is giving us gamma of st, then lambda, then f of t dt. So this free term is known, and resolvent kernel 2 is known by what? Adding all the kernels, you get a resolvent kernel. Then this side 2 is known. Then you can easily what? Compute for the solution for the Fredholm's integral equation. So anytime you are given a Fredholm integral equation and they ask you to use the approximate method using the kernel, first you need to know that one, know of your kernel. The n of your kernel, k of nt, is always giving us integral of a to b, then k of s, then k n minus 1 of s, t ds. Then the next thing is that you need to add all the kernels you are going to get, which is called the iterative kernel. K1, K2, K3, K4 up to the K, and are called the iterative kernels. So if you sum all the iterative kernels, you are going to get the resolvent kernel. S of t lambda to be equal to, then our k1 of st plus k2 of st, lambda is here, plus dot 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 plus what? Lambda n minus 1 k of n of what? St, which is the same as summation of what? N is equal to 1 to infinity lambda n minus 1 k of n st. And the third one you have to note is that your solution becomes phi of what? S equal to f of s plus lambda integral of what? A to b. The resolvent kernel s t lambda f of t dt. So anytime you are giving a further integral equation that use the approximate method using the kernel, these are the three terms 1, 2, 3 to note, and how to get the result, how to prove all these things. So in our next video, we are going to look at some examples in the approximate method using the free term and using that of the kernel.